homework for Math 1, 10.2 counterexamples. Use the illustrations, explain in sentence form, or use algebra to show that each conjecture can be true. Then show a counterexample, illustration, well-written logical sentence, or algebra to prove that the conjecture is not always true. Complete on a separate piece of paper. All right, so did you guys do that? Separate sheet of paper? I don't see any separate sheets of paper out. All right, so first we want to show how it can be true, and then we want to show a picture of how it could be false. All right, so if it is 12 noon, then the sun is shining. I don't know how we have to draw a picture of that, but we could draw a sunny day, obviously. Probably most days in the summer in Fresno, it is a sunny day at 12 noon. But if you were in the middle of Seattle, yeah, Seattle has the fewest sunny days of any city in the United States. So Seattle, probably the odds are it's 12 noon, it's not sunny, because they spend most of their year covered in overcast clouds. Okay? Questions on number 1? So Fresno, most likely sunny. Seattle, most likely not sunny. Good? For number 1? Okay, so you should write out you might be in Seattle at 12 o'clock. If the car is full of gas, then the engine will start. What might you write down for that? Yeah.
There might not be an engine in the car.
There may not be an engine. Gotta have spark plugs, right? Maybe there's no battery. Maybe the battery's dead, right? A lot of options, so you need to write something down there. Number 3, if a number is divisible by 3, then it is odd. So pretty easy. What are you going to write?
30.
About 12. 12 is divisible by 3.
30.
30 is divisible by 3.
6.
6. Okay. Any multiple of 2 and 3. Okay. Let's see. What are we next? The sum of 2 integers is always positive. Sum of 2 integers is always positive. You guys got an example? Oh, you guys are on fire. -3 plus -3 is -6, right? Integers are all the positive and negative numbers. The product of 2 mixed numbers is never a whole number. Product means multiplication. Mixed number is like 3.5, right? So the product of 2 mixed numbers is never a whole number. What did you guys come up with? Anybody? Nobody? Nobody's got anything? Nobody came up with one. 2 mixed numbers. What you got?
2 1/3 and 8 2/3.
Ooh, wow. Let's see. Before I write that one down. 2 1/3. Oops, 2 1/3 times.
Oh, no, I did addition.
Okay, product multiplication. Well, what if we did this? What if we made those mixed numbers? Instead of mixed numbers, aren't mixed numbers also improper fractions? Okay. So, what's that? So what if we had, let's just go, so when you multiply mixed numbers, you multiply the numerator, well, when you multiply improper fractions, which are mixed numbers, you multiply the numerators, you multiply the denominators, and then you can divide, right? Or reduce. So what's 2 times 3? 6, okay? So we need two numbers up here that are divisible by 6. 3 and 2 would work, yeah, but that wouldn't give us mixed numbers. 6 and 12, I like that. Oh, well, oh.
3 and 6.
Let's go with, how about 5 and 5 and 6 won't work. Can we come up with 5 and a mixed number, though? It's not a mixed number. What do we got to come up with? What if we did 15 here? And then we've got to go 2, 4. 4, there we go. 4 would do it. There we go. And this is 60, which is 10, right? So our mixed numbers have got to be, what do we got? 7.5 times 1 1/3. Oops, not equals, times. Does that make sense how we came up with that? Okay, so you don't always, probably just coming up off the top of your head thinking of two mixed numbers would be pretty difficult. But if you change those mixed numbers into something that looks a little easier, like we did, we converted to improper fractions, and then we turned them into mixed numbers. Okay? So what do we got here? We've got 7.5 times 1 1/3 equals 10. Does that make sense? All right. Number 6, all four-sided figures are rectangles. Well, it's just the opposite of what we did, right? We could draw a square. Now, here's the important thing about geometry. Is that a square? It kind of looks like a square, but I don't know if I did a great job. So to show that it's a square, I'll just do that. So in geometry, you have to trust your picture, or trust what they tell you, I guess, more than your picture. You have to trust the explanation more than the actual picture itself. Meaning sometimes we'll give you something that looks like a 90-degree angle, but we tell you it's 80 degrees. You just have to trust what you're told. It's called the given information. You have to trust the given information. Okay, number 7. This is one you had a tough time with. The product of two positive numbers is greater than either number. The product of two positive numbers is greater than either number. Ooh, is there a counter to that? Well, what if we just use 1 as one of our positive numbers? Is 3 greater than 3? There's your counterexample. Okay? All right, number 7. Oh, we got more going on here. Oh, we're having a little explanation here. Okay. To start, write a statement that describes a counterexample. Find two positive numbers with a product less than. What are we doing here? Find two products. I don't know what that is. I don't care about that. The difference of two integers is less than either integer. The difference of two integers is less than either integer. Is that difficult? Less than either integer. Well, easy one would be 5 minus 7 would be -2, right? The difference of two integers is less than either integer. Yeah, that works, right? Oh, yeah, you're right. You're right. Sorry. That one was confusing me. Okay. So the difference of two integers is less than, oh yeah, okay, I'm thinking of it backwards. Well, we'll go with a negative number. How about that? 5 minus negative 7. There we go. Which is 12. How's that one? That's better. Thank you, Mr. Montoya. Your parting contribution. Okay. And number 9. We know that AB is equal to BC. Okay, so that's actually the length of AB equals BC. Conjecture, B is the midpoint of AC. Draw, okay. So a counterexample. Wait a minute. Known, AB is equal to BC. Okay. Conjecture, B is the midpoint of AC. Okay. What do they want there?
They just want us to show that B isn't the midpoint of AC.
AB, BC. Oh, B is, okay, let's see here. So let's draw. There's B. Oh, that is not a midpoint of BC. Okay, yeah, okay, I got you. All right. So we've got AB. We'll do it this way. A, B, and C. And we can show those two are congruent. There you go. All right. And so AC would be right there. Okay. And what would the next box be? So we had a box, we drew a line, then we drew another line, and then we drew two more lines. So what's our next box going to look like? So we had a box, then we drew one vertical line, then we drew one horizontal line, and then it looks like we drew a vertical line on either side of the horizontal line. So we drew a vertical line, then we drew a horizontal line, then we drew a vertical line on either side of the first vertical line. So what are we going to do next?
Two horizontal lines.
Draw a horizontal line on either side of the horizontal line. Now the next step, I don't know what we do from there. I don't know if that means you add one, then add two, then probably I guess we'd add three the next time. Okay, so it seems like I did most of the work on that. All right, so let's do Math 1. All right, Math 1, Unit 10.3 to 10.4, conditional statements. Conditional statements have two parts, a hypothesis and a conclusion. Conditional statements can be written in if-then form. So what we usually say is if the hypothesis, then the conclusion. All right, so it's if-then statement, but we always have, well, our conditional statement is always if the hypotenuse, then the conclusion. And a real short way of writing it is if P, then Q. All right, just a way to really condense it down. If P, then Q. All right? So the converse of a conditional statement is just switching the hypothesis and the conclusion. So the converse would be if conclusion, then hypothesis. Okay, all we did is we switched these two guys to write our converse. And the shortened version, you can see what we're doing here. Took our Q there, and we put our P over there, so it's written as if Q, then P. All right? So let's try to write a conditional statement and the converse. Write a conditional statement in if-then form, then write the converse. So our statement is a straight angle measures 180. So we can write it like this. If an angle is straight, we can write it like that. Or we could write if an angle is a straight angle, then it measures 180 degrees. Okay, almost ran out of room. I wrote a little too big at first. If an angle is a straight angle, then then it measures 180 degrees. Okay? So our hypothesis is right there, and our conclusion is right here. So to write the converse, we're going to leave this part right here. We're going to leave that because that's not really part of our hypothesis. So we're going to write for the converse, we're going to write if an angle measures, right here, 180 degrees. So we took the conclusion, we put it right here. Then, now the hypothesis, it is a straight angle. Okay, does that make sense? Any questions on that? Our hypothesis in the first one is if an angle is a straight angle, the conclusion, then it measures 180. To write the converse, we simply take the conclusion and put it first, and we take the hypothesis and put it second. If an angle measures 180 degrees, then it is a straight angle. Now, obviously, sometimes you got to change the grammar around a little bit, but I'm a math teacher and I don't really care about grammar much. So if you literally just pick these words up and put them here, take these words and put them over there, even if grammatically it's not perfect, I really don't care. All right? Just want to make sure you understand. All right, number 2. Write the statement in if-then form and write the converse of the conditional statement. Decide whether each statement is true or false. So, guitar players are musicians. So, there's our hypothesis. And there's our conclusion. So we'll write it out maybe a little bit better. We'll say, if you play guitar, then you are a musician. Does that sound true? If you play guitar, then you are a musician? That seems true, doesn't it? Okay, now let's take the conclusion and write it first, and then the hypothesis and write it second. So now it's if you are a musician, then you play guitar. Okay, is that a true statement? It's not. You might play any number of other instruments. So we'll put true here, and we'll put false here. Okay. Now, if the converse, if the conditional statement and the converse are both true, then we can write what's called a biconditional statement, which is very concrete. When you can write a biconditional statement, you know that rule is always true. Okay, it's very concrete in geometry. So a biconditional can be written if the conditional statement and the converse are both true. Written as P if and only if Q, where remember P is the hypothesis and Q is the conclusion. So we would write the hypothesis and then if and only if the conclusion. So in problem 1, let's go back to problem 1 real quick. You'll see that if an angle is a straight angle, then its measure is 180 degrees. That's true, isn't it? Hopefully you remember that from unit 7 or 8. Not sure. Okay, and then the converse is if an angle measures 180 degrees, then it is a straight angle. That is also true. So even though we can't write a biconditional for number 2, we can write one for number 1. And we just simply write we'll have if an angle, Susan, we're just going to say if an angle, we're going to write an angle is a straight angle. So right here, we're going to leave off, all we're going to do is cross out basically the if, and we're going to cross out the then, and in place of then, we're going to write if and only if. So we're going to write, I'll move it up here so you can see an angle is a straight angle an angle is a straight angle, and now we write this little if and only if, and then we write the conclusion, which is it measures 180 degrees. So if you read it all together, it sounds very concrete. An angle is a straight angle if and only if it measures 180 degrees. That's pretty specific, isn't it? Okay? Everybody got that? All right, we ready? Let's see what we got here. Number 4. All right, definitions are often written as conditional statements. Write the definition of perpendicular lines as an if-then statement. Then write the converse. Then write the biconditional statement. All right, I'm going to give you a couple minutes to do that on your own. I'll give you about 2 minutes to write the if-then statement. Remember, we're talking about perpendicular lines. What do we know about perpendicular lines? Perpendicular lines intersect at 90 degrees. Okay, so that's your statement. Turn that into an if-then statement. If hypothesis, then conclusion. Once you've done that, just simply leave the if and the then where they are and pick up the two and switch them. If they both sound true, then it's simply hypothesis, if and only if, well, actually you got to put them back first. Hypothesis, if and only if conclusion. Ready, break.